record and broadcast session, and you are good to go.
Okay. Hi, everyone. Okay, hi, everyone. My name is Bisola, and today we're speaking on from theory to reality, the journey of quantum computing. And today we are going to be speaking on basically, historical foundation of quantum computing and how it has, come to be. So the new era of quantum computing. So first of all, for decades, computers have helped us to work faster and smarter. And some problems are big, are like, the current computing technology, in a way, has helped us to work faster. Before, to send an email from, say, from UK to Africa probably would require some bets, training, or basically months of traveling across the sea. But however, we can do that today within in less than a minute. So this is what classical computing has done for us, or the computers we know it today has done for us. But there are some problems the current computing technology we have today cannot do for us, in terms of, say, simulating nature, in area of drugs discovery, like decoding complex molecules. That cannot be done. And that's where quantum computing steps in. Is sort of like a new way of thinking about information, right? So moving on to the next aspect of quantum computing, where we are, talking about, what makes quantum computing, what makes it different from what we have today. So the regular computing technology we have today uses the binary digits, which can either be 0 or 1. However, quantum computers the quantum computers use qubits, or we call it quantum bits, which can be both 1, 0, and 1 at the same time. So what this means is that so the regular computing technology, in terms of 0 and 1, we can say the bulb can be on and off, right? It can be on or off. The bulb cannot be on and off at the same time. But using the same example with the quantum computers, it appears as though the bulb can be on and off at the same time. So that's a higher level of technology. And this means that we can, process massive amount of information at once. So what's the science behind quantum computing? We have superposition, and just before I move ahead, quantum computing is basically based on quantum mechanics and physics. It follows strictly quantum laws. And so the core science, or the core principles behind quantum computers are these three principles. We have superposition, entanglement, and interference. And so for superposition, it in a way it's kind of like help. So I'd given an example before about how quantum computer, or quantum bits, the qubits can be 0 and 1 at the same time. So superposition is the technology, or is the principle behind that. There's also the entanglement, which is two qubits can be connected. So it helps the two quantum bits, or say two quantum bits that are connected. It helps them to react instantly if there's any change in one. So if there's been a change in one, the next qubit can react instantly. And following this principle, it means that if, say, there's a technology across the world, and that is running on quantum technology that are connected, if there's any change in one technology, it's going to instantly affect the other one. There's also the interference, right? That has to do with the quantum waves. It kind of combine So what this means is that when we have, so let me give an example. Say a ChatGPT that runs currently, if you were to run on quantum computing, you are most likely going to be getting right answers when you want to do your research, when you want to ask questions, because there's a way this principle of interference helps to cancel the wrong ones out, right? And that's the science behind it. Then I'm just going to give, the historical foundations of what quantum computing, how it came to be. So we have in the 1980s, there's the birth of quantum computing or the quantum thinking, which is really about, there's the physicists, the scientists, they came together, they proposed uh, they proposed um, they proposed that computers could follow the strange rules and, oh, excuse me.
Yeah, I was going to say your slides don't seem to be moving. Are they supposed to be? Just sorry to interrupt.
Yeah, I saw that. If you don't mind, excuse me, please. Let me just try to. I timed it and then that was. Okay. So.
You may be able to just manually go through them at least so that we can see them changing.
Yeah, so just try and going through hand. Basically what we have in the so we have the birth of quantum computing basically, which is, oh my god. Oh, apologies. Okay, so we have the birth of the critical thinking. Oh, this is timed and so yeah, we have the mathematical. So from the birth, so we have the initial creation of how quantum computing came to be. So the initial slide that talks about it came about when two scientists, they came together to say, you know what, is it possible that we have computers where we have computers that run on quantum laws, and then that just started coming up with different, questions. There were a lot of presentations and a lot of research around that. And then, that was in the 1980s. And then we now moved to 1990s, where it's basically the mathematical breakthroughs. And so the current algorithm we have today that quantum technology runs on, they were developed in 1994 and 1996 in sort of way, and which kind of threaten the classical computing as we
Sorry, your slides aren't moving still. Apologies. Just in case you think they are, they're not visibly moving unless anyone else can see them moving.
Okay, the slides are not moving.
They're not moving at all. No, you're still stuck on the first page for me at least. There you go. Yeah, now they're changing.
Oh, okay. Okay, so can you see these now?
Yeah, I can see you're now on slide number 10, but before you were always on your title page. But that's, yeah, just.
Oh my. Sorry, I didn't.
No worries.
And I just kept. So I just had to.
You can just manually use the slider. Yes, Mariam, exactly. Yeah.
Okay. Yeah, apologies everyone. I thought I was actually, I just kept going on and on. So maybe I might just as well just, start from the historical foundations and, just try to run it through. So there's the 1980s, that talked about, can you see my screen now on the 1980s?
Yes,
please?
we can.
Okay, yeah, thank you. Okay, so we have, the 1980s, the birth of quantum computing, where we have scientists that actually, came to, ask questions about, quantum computer. Like I said earlier, do we have computers that can run on quantum mechanics or quantum laws? And and then that actually started, that brought about what exactly is, quantum technology. And, we have also in the 1990s where the quantum algorithm, was created. And we saw that, there's another technology that could be faster than, classical computers. And we also have the Grover's algorithm, and they are still in use till today. So in the 2000s, we have the first quantum experiment, which I would say, 2001, it was really a massive milestone, where we have IBM built a 7 quantum built liquid state quantum computer. So that's actually like a big deal. And the quantum computing, it moved from, the theoretical aspect, the lab, the lab experiment to, or from the theory to real physical experiments where we can now, we can try to build something, around this technology. Then in 2010, so from 2010 to 2019, we have the D-Wave systems launched the first, it launched the first commercial quantum processor. Then we also have IBM Quantum Experience. They made quantum computers available online in 2016. Then in also 2019, there was a fantastic, development around, there was a task that was solved in 200 seconds by quantum computing technology. And that would have taken the current technology we have today thousands of years to solve. So that's a big milestone. And yeah, so in 2020, as a current year or the current duration we have, what we now see is there's now a sort of like a quantum race. The IBM, Intel, they are competing to, build larger, more stable quantum processors. Nations are investing heavily in quantum technology. Like I know of India. India is, trying to, there's something called, I think there's a latest article on India Quantum City. They're trying to heavily invest in that. China is leading the race. America is also, they're trying to invest heavily in quantum technology. And, as we have it today, we are now in the noisy intermediate scale quantum. Yeah, so in history, this will be called NISQ era. So that's the official era of what we have it in quantum technology. Even though it's kind of imperfect, the quantum computers, they are kind of error prone. They have a lot of challenges, which we are going to be discussing, later today. But, but this is what we have today is that powerful systems are actually being built, even as we speak. Then today, the future unfolding, we have a lot of researchers, they are, or what people are doing currently today is that researchers are pushing forward, or they are pushing towards fault-tolerant quantum computers. Because what we have today, as much as this technology is so powerful, even more than the current technology we have now, the problem is error prone. That it has a lot of errors. The error rates are high. So, and it had to, the heat, the noise, and it's quite noisy, right? It's a noisy technology, just like when classical computing was initially built as well. So, this is what researchers are seriously working on. And we now have industries, companies in finance, in medicine, in AI. They are saying, you know what, they need to explore how this technology can reshape their fields, right? So, just in a way to say that, from 1980s to 2005, as at today, this technology has evolved, from from a simple question of can we have computers that run on quantum mechanics to now saying, oh, we need to even develop on this technology to building, real computers, like physical computers that run on the technology. So I would say that this has really grown, or this technology has really grown. So just as a note of emphasis, because this is what we have now. We have the noisy intermediate scale quantum computers. We have current devices. So for an average, it runs on an average of 50 to 500 qubits. That's when I say qubit, that's quantum bits. They are noisy and error prone. Yeah, so that's one of the very fundamental challenges. One of the very fundamental challenges we have in quantum computing. And also, as of today, scientists and researchers, they try to mix quantum computing and classical computing to be able to get useful results. And yeah, so basically, and what we have today is like we can compare it to what we have in the 1940s for classical computing, where people were asking questions that is it really possible for me to communicate to somebody across the world, across the different oceans around the world? Is it possible for me to do that with just a little device? Is it possible for me to do that? But what we have today, that's what exactly is happening today. So that's the stage quantum computing is at the moment. Then we have the current challenges in quantum computing. And so where the challenges still exist, right? One is unstable qubits. So we know that due to the heat, noise, and interference, and the qubits, or the technology that processes and store information on the quantum computing technology, it loses information easily. So that's one thing to note. Then also the error rate. Even the top machines built by IBM, Google, and all of these other companies that are, building, they kind of make frequent mistakes. Error correction as it regards to quantum computing is still limited. Then also there's the scalability problem. So it's kind of hard to build and control thousands of qubits, consistently compared to what we have in classical computing. Then some of the challenges also include hardware complexity. So we have most computers, they must be cooled to near absolute zero temperatures. So they need to be cooled, just like I think that's what we used to have in quantum computing, classical computing, where we have this massive computer where they need to have AC and all of that. So that's what we are facing currently too in quantum computing. There's also the current algorithm, like the Shor's algorithm, the Grover's algorithm, they kind of have a little limitation, right? And some algorithms that have been developed, they are still experimental. They are still at the experimental stage. There's also the high cost of computing, right? So the quantum systems cannot be built by an average company. I mean, you need to have a lot of money to be able to invest as we speak today. So millions of dollars, if not billions of dollars as well. So that's why the development is kind of restrictive. Nobody's talking about it compared to artificial intelligence. And so just to say, quantum computing is very powerful, but still fragile, costly, and there's loads of unanswered questions that scientists, researchers, they're working on daily just to be able to make this technology become, usable to everyone. Now, so, talking about the history, a lot of stuff around the quantum computing. So we have, oh my God. Okay, so we have the future applications that talks about how quantum will transform industries. So we have, a lot of people probably here that probably they are interested in how will quantum computing, how will it transform industries? Or how will it affect my industries? Or, all of this talk, how does it concern me really? Yeah, so basically, in terms of people in cybersecurity, or people in computer science field, this might be of interest in terms of the impact on cryptography. So so in today's world, there's a technology that protects everyone. It protects everybody uses computers, right? There's a technology that protects the communication between one computer to another that at least makes us all safe. And that's what the attackers or the hackers try so much every day, just to break and try to see, if anybody can even, just looking for different ways to actually break this technology, right? However, when we have quantum computing, the current encryption is not going to be useful. So this is not the current my router at home. My home router is safe. The corporate IT environment is safe. It's no longer going to be like that. So what we have at the moment is that we have researchers and scientists working on a quantum safe, systems as well. Then advances in medicine. Definitely, there's going to be massive drug discovery and also in medicine. Then in finance and in also logistics, you're going to see a lot of finance portfolios being optimized, and also there can complex logistic issues like global shipping routes and scheduling problems can also be solved. Then in terms of enhancing artificial intelligence, so with quantum machines, it may be able to detect patterns that are missed by the current computers that we have. Also, yeah, so the next stuff we are going to talk about is the ethical and security considerations. So in terms of, even though quantum computing is a big technology, it's going to make a lot of changes to, probably it's going to affect probably every field, right? Almost every field, because it's going to upturn the fundamental way of communication. Communication is going to be faster, using the internet and all. But there are still some questions, that people are asking, or policymakers are asking, in terms of ethics, access, and security. For privacy risk, encryption involve, so there's a talk around encryption as we know it. So encryption, like I explained earlier, kind of the current technology that protects the computers communication we have today. So it must evolve before quantum computers outpace. Then secondly, the fair access, right? So company, they share progress instead of holding it. That's also very important. You know, uh, we also have the ethical use where transparency is also encouraged. There's also the global policy that talks about, and that's safe and fair, fair quantum. So, really, before I round up, I just want to talk about the opportunities in quantum computing. So I know that a lot of people might just be asking, so in how does this concern me, or how can I even start how does this relate to me? Because okay, all of these things are coming, big stuff, good, but how something like that. So that's why I've put this together, that how can you be part of the quantum future? If you're a student or you're an early learner, you can join. There are a lot of forums to join. One is Qubit by Qubit. There's also the Quantum Open programs. There's also the there's also the IBM Quantum Experience, and Amazon brackets that run real experiment online. That can also be, also used, or that can also be joined. Then also in terms of introduction to quantum computing, there are a lot of courses that are actually available for beginners to start learning about quantum computing. There also, we have hackathons, there's STEM clubs, school science fairs are also beginning to show interest in quantum computing. So for university students and researchers, lots of internships and fellowships with IBM, Quantum Labs. You can also join campus quantum research, assist with simulation projects. You can also explore PhD placement in quantum computing or, cryptography or material science, as it is. Then we have the started in quantum computing. So started in quantum computing, or maybe you're a professional. For most professionals, they probably would join, some of these forums that I've mentioned, but they might want to, okay, so how do I even start? One is you could strengthen your, if you've not started learning Python, I would advise that, anyone start learning Python, or the person that's interested start learning Python, and also learn a bit of linear algebra and probability. Then also study quantum concept through YouTube channels. We now have YouTube channels called Quantum Country, and loads of them on YouTube channels. So just to learn about quantum concepts. Then also there are a lot of communities, the ones that I mentioned earlier. We have Quantum Computing UK, IEEE Quantum, G World, Women in Quantum, etc. Then also there's online meetups and, global hackathons. They are free and also beginner friendly as well. So someone can join that. And very importantly, it's very important to, it's very, 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 would I say good, or as much as you're learning, it's also good to build portfolio in terms of share your small quantum project on GitHub or write posts on LinkedIn or Medium. Also, there are a lot of certificates, micro courses that are free. Yeah, on some of these platforms, not all though, but some of them are free, short courses that can be taken and certificates can be earned, right? And yeah, so that's basically how to get started. Then for the conclusion, the quantum era is here, but not for those who wait, but for those who dare to explore. So I don't know if there are any questions or anything at all.
Thank you so much for that. That was really great. I like the information at the end about how to get into quantum. That was really useful. Are there any other questions for anybody? You can either drop it into the direct chat, or there was the Q&A section as well. I can't currently see any. Awesome, thank you. There's a question, one question. What do you think is one of the least known, misunderstood aspects of quantum computing?
Okay, like misunderstood
What do you think
aspect
is
of
one
quantum
of the
computing?
least known, or in other words, misunderstood aspects of quantum computing?
So there's this in cybersecurity, because that's where I'm specialized. And there's this aspect that when quantum computing comes, is going to actually, break the current encryption, or would I say the current cryptography that we have in the world today. However, that's not necessarily true, actually. So it's just that it weakens the current would I say the current encryption technology that we have today is probably going to weaken it. And why is it like that? Because it's so fast. It's going to be so fast, and it's going to be working on, like I said earlier on, what's happened on the Sycamore processor, where a task that would take the current technology thousands of years to solve was done in 200 seconds, And so that's where we are going to. That's the world we are going to. That's the future. So it's definitely going to weaken the current technology that protects computers. So that's what we have. It's going to weaken it, but then we now have a lot of development around making sure that the computers in the future that are going to be running on quantum computing are going to be safe. So we now have the post quantum cryptography. That's what we have today. Yeah. But there's this buzz around, oh, quantum computer is coming to do this, is coming to do that. Do we even need to start exploring this technology now? There's a lot of stuff around that. But then it's going to come just like what we have today in classical computing. Before, in the 1900s, there was no way anybody could imagine that within a second I could get across. I could talk to somebody in America from the UK, or in Africa from the UK in less than a second. But now we have that now. And the funniest thing that for every technology, the human being that exists at that time, we adjust. So the mindset would adjust, the behavior would adjust, and then we are able to cope with that technology.
Thank you. Thank you for the question. And the next question is, how does quantum computing create value in the AI and machine learning development journey?
Okay, so for artificial intelligence, so when you say artificial intelligence, I'm guessing the person that asked the question is talking about generative AI, because what we have today, maybe ChatGPT and all of that. So for the ChatGPT, the principles of quantum computing that I spoke about earlier on how it's going to make things very, very fast. So as you're asking the question, there's no need for, we have what we have currently. ChatGPT thinks that if you want to get better answer, you need it to think a little. That's probably not going to happen again. And secondly, in terms of artificial intelligence as it relates to current technologies being built, automation, for example, it's also going to be faster. Things are going to be automated. A lot of jobs we have today are going to be automated because we now have a computer that can solve problems. And even in, say, in medicine, there's going to be a whole lot of drug discovery. Maybe some diseases that we have today that they appear that they can be, they are what I call it uncurable. By then, there's going to be some drugs for it. I mean, medicine in quotes, medication for it. Yeah. So for artificial intelligence, the computing power is going to be faster for sure if it's running on quantum computing. That's as it relates to generative AI. So you are able to interact more. And we have a lot of robots, being built now. They are going to be maybe more powerful than they can now do tasks that normal human beings can do, because that's definitely going to affect it. So it is a whole new technology. Maybe the world then, I'm trying to see that the world then maybe a little bit scary because the technology is quite powerful.
Okay, I think we're at the end of the session. So we have, thank you for that. That was really great. There are a couple more questions in the box, but just because I'd like to keep it moving a little, I will probably just ask one more and then we can wrap it up after that. The last question was, are there any problems in your day-to-day that you would like to use quantum computing to solve?
Okay, for quantum computing. So what we have, that's one of the major problem we have in quantum computing. As we speak, it doesn't relate to the day-to-day activities of humans. Basically solving the big problems, trying to basically talk about or solve. For example, in logistics, it's going to help work on the global shipping routes. So yeah, so better on that. The goods on the sea can probably be better, or the ships themselves can also move faster on the sea. That's what we have today. Just like artificial intelligence. Artificial intelligence didn't just come up today. Before ChatGPT, it's been there. Even for in my field for cybersecurity, for threat detection, there's been artificial intelligence for years, right? But just that why there's the buzz around artificial intelligence, because there's the day-to-day activity. Humans can now use it for day-to-day activity. And that's where quantum computing, and that's what researchers or scientists are working towards. But it might take a long time. Not necessarily it's going to happen tomorrow or next, but I think it's going to definitely get there, where you can now talk, or the computing, or should I say the technology that powers the day to day, you can now say, oh, it's quantum computing and all that. Say, but it's not something that is happening now.
Okay, amazing. Thank you so much for that. I will say, yeah, thanks for that. If you want to go to the lounges, everyone can go to the lounges for a bit to kind of network, and I'm sure maybe Bisola will stick around for a little bit, and you can answer any other questions if anybody has any. And then the next session will begin at 7, I believe. So thank you very much. Thank you for that. Thank you for that talk. All right.
All right. Thank you.
Bye, everyone.
So.